in 3.1, example 2 starts talking about some of the basic characteristics of polynomial functions. And again, this is in your textbook if you want a high quality version of this. And at least what we're going to begin talking about is the end behavior of that function. End behavior is what happens when x becomes very large in the positive direction or very large in the negative direction. We're not going to look too much at degree 0. Degree 0 is just a horizontal line. That's like y equals 3 is what they have here. Linear functions are odd degree. And when x is very large, it extends up into quadrant 1. When x is very large in the negative direction, it extends down into quadrant 3. And what I'd like you to look at is if we look at an odd degree function, so this is degree 1, here's degree 3, and here's degree 5, all three of those have the same end behavior. Right? If we think about what is happening on that graph, they are both extending from quadrant 1 to quadrant 2 and moving in that direction kind of indefinitely. And that's going to be a really important consideration, is that once you understand the end behavior of odd polynomials, all odd polynomials follow that. Now, a really, really big caveat is in green here. What happens when the leading coefficient is negative? And if the leading coefficient is negative, it is very much like what we talked about in chapter 1 and 2, that it would be a reflection across the x-axis. So if the leading coefficient was negative for degree 1, my function would look like this. For degree 3, it would look something like this. For degree 5, it could look something like that. Now, one of the other things that's, I think, really important to talk about is that the degree of our polynomial corresponds with the maximum number of x-intercepts, not the minimum, and that's really important. I just want to quickly draw. I could draw a cubic that looks like this. That only has one x-intercept, but I would never be able to draw a cubic that would have 4 x-intercepts. And the best way to understand that is the degree is really the maximum number of factors, which would be the maximum number of values of x that would cause it to be 0. What I often push students to do when we're dealing with this end behavior is to memorize degree 1, 2, 3, and maybe 4, and then just be able to extrapolate based off of that. So if we look at the even degree polynomials, and they only have, technically degree 0. Degree 0 is a bit of an exception here. So degree 2 and degree 4 are both even degree. Look at their end behaviors. If the leading coefficient is positive, they extend up in quadrant 1 and quadrant 2, and both of those graphs do. If we made the leading coefficient negative, then it would do, maybe not the opposite, but it would extend into quadrant 3 and quadrant 4. And maybe that's an oversimplified version on the bottom there. I'm just going to draw it, and it looks something like this. A nice kind of shortcut to be able to identify what degree it is from the graph is that degree can correspond with the number of direction changes. So if we look at this degree 5, we have 1 direction, 2, 3, 4, 5, and it corresponds with that quintic or degree 5 function. What we're going to use this for is to quickly evaluate what potential graph, or what potential equation I should say, the graph has. And the best way to do that is based on the graph, we can identify whether it's odd degree or even degree, and then we can look at the number of possible x-intercepts, whether it has a max or minimum, and then finally we can match each corresponding graph below. All right, so looking at A, and I'm just going to put the little arrows on it like this. If I look at A, this has degree 3, and because it's extending from quadrant 3 to quadrant 1, I know it has a positive leading coefficient. When we talk about the number of possible x-intercepts, there are 3 possible x-intercepts. Keep in mind that possible doesn't mean required. That particular graph actually has 2 x-intercepts, although one of them has a multiplicity, which we'll get into a little bit later. Now, if you have an odd degree polynomial, it cannot have a maximum or a minimum. And the logic behind that is if you think about this odd degree function going from quadrant 3 to quadrant 1, it's never going to have a min or a max because the range is all real numbers. And that's going to be an important consideration. So I'm just going to put no min / max. And then the y-intercept, that's a scale of 12. So it looks like maybe 1, 2, 3, 4. I'm going to say the y-intercept is somewhere at 0, 4. And that's, kind of rough. If it ends up being a little bit off from that, we can roll with that. And we actually get a little bit lucky here because there's only one cubic function in the list. So graph A is the function. I'm going to write it underneath. F of x is equal to x cubed plus x squared minus 5x plus 3, and I'm actually going to modify my y-intercept because now we can see that it's at 0, 3. Now, because that was the only cubic, that made it a little bit easier to see which answer was going to match with that. The other ones we probably won't get quite as lucky. All right, for option B there, again, just trying to think about that direction change. It goes in 1, 2, 3, 4 different directions. So that indicates kind of the minimum degree. So it has to be degree 4. Because it's extending into quadrant 2 and quadrant 1, that looks a lot like y equals x squared or y equals x to the power 4. So again, we know that it has a positive leading coefficient. The number of possible x-intercepts, it could have 4 x-intercepts, and it does have 4 x-intercepts. There's 1, 2, 3, 4. A little bit off on the marker, sorry about that. It can have a minimum or maximum. So what we need to do is use the graph, and we do see that this point down here is the lowest point, so this graph does have a minimum. When we talk about even degree polynomials, they will have a maximum or a minimum, but not both. And that's due to the end behavior of that function. The y-intercept, again, I would be guessing a little bit. I'm going to say that that y-intercept is somewhere, I don't know, I'm actually cheating a little bit here. I'm going to say negative 12. So my y-int is at 0, negative 12. Now, looking at the information we only have 2 coordinates to choose from. We have g of x or we have h of x. We know that it must be h of x because of the leading coefficient. If I look at graph B, because it's extending into quadrant 2 and quadrant 1, when x is very large, the value of the function is very large. So this has to be the graph, and I'm just going to put h of x down there. All right, moving right along, we look at graph C. We'll do the degree first. I'm going to do that direction change again. So 1, 2, 3, 4, 5. So this is the minimum of degree 5. Looking at my end behavior, and I'll draw it up here. And I always like to go back to y equals x cubed because it's nice and easy to draw. Y equals x cubed goes from quadrant 3 to quadrant 1. My graph doesn't, but it has to be an odd degree. So we know that we have to have a negative leading coefficient. And I'll write that up here, that this is y equals x cubed. If I were to flip it, and I drew the same thing, which is just genius. If I were to flip it, I would get this, and this could be described as y equals negative x cubed. I mean, they're not exactly that because y equals x cubed is very simple, but the end behavior would look like that. Okay, negative leading coefficient. Looking at that, because it's degree 5, we would have at most 5 x-intercepts. And we actually do have 5. We have 1, 2, 3, 4, 5 unique ones. Because this is odd, there is no min or max. And I really do like pushing those concepts that as soon as you understand whether it's even or odd, that can really guide you as to whether or not a minimum or a maximum is possible. Now, we'll learn later on in calculus that there's other points called local maxes and local mins, and any polynomial can have those, but that's not what this question is asking. All right, the y-intercept. To me, it looks like that's going right through the origin. So the y-intercept is at 0, 0. Now, the one thing I'd like to point out is that the y value at the y-intercept corresponds with the constant when we deal with these functions. Now, we're getting a little bit messy here, so I'm just going to kind of cross out some of the ones we've done. We've identified h of x. We've identified f of x. So it's a toss-up between p of x and g of x. And hopefully it's not much of a mystery. Because this is degree 5, this graph C has to be the graph of p of x. And we do see that p of x has a degree 5, a negative leading coefficient, and a constant of 0. All right, now, of course, process of elimination, we all know what this final graph is, but I do want to go through the process all over again. Looking at this function, it has 1, 2, 3, 4 different directions. So the degree is at least 4. I'm just going to erase that again. It looks so weird having it on there. Because, and I mean, I would look at graph B if I were you. Look at the difference between the end behavior of graph B versus graph D. The reason they're different is that graph D has a negative leading coefficient. All right, this could have 4 x-intercepts. It does have 4 x-intercepts. And because it has a negative leading coefficient, it now has a maximum. There is one point that is larger than any other point on that function. The y-intercept, I'm going to cheat again. It's actually at 0, negative 4 because this is the graph of g of x. Now, this section in chapter 3 is very, very general. It's talking about just some of those behaviors, but I really don't want you to kind of understate the value of it. Knowing the end behavior of functions is a really good way to predict what's going to happen when we model a real situation using that function. And that's really what most of this math is about at the end. Oh, wrong button there, sorry.